why magnetic fields are so useful is their ability to exert forces on electric charges that are moving. So stationary electric charges don't see the magnetic field, but as soon as the charge starts moving, there will be a force on it. And one example of charge moving is of course electric current. So in this illustration we have a conductor that is placed in a magnetic field as shown here. And because these charges are moving in the conductor, they will be pulled to some direction, which means that that pulls the conductor with them along as well. You might be tempted to think that in this case the conductor would align itself with the magnetic field line, but that is in fact not the case. The situation is different from electric fields, where the force was along the electric field lines. But in the case of magnetic field, the force in fact is given as follows. We are expressing this in the vector form, that is the most general one. So it states, if there's a current I going through the conductor, the force will be the length vector, which is directed along the conductor and into the direction of the current. And the magnitude of the L vector is the length of the conductor. And this vector is cross product with the magnetic field vector. In essence, this equation tells us that the direction of the force is perpendicular to both the direction of the current and the direction of the magnetic field. If you're a little rusty with your vector algebra and cross products, then here's how you do it. In this comic here, we would like to evaluate the cross product C, which is the cross product of A and B. So you take your right hand and point your fingers along the first vector, in this case A, and then you curl your fingers towards the second vector B, so curling in this direction. And now when you hold your thumb up, that will give the direction of the C. Again, point to the direction of the first one, this one, curl towards the other one, and your thumb will tell the direction of the third one. We are of course also interested in the magnitude of the force, F. And it follows from the magnitude of this cross product. So we have I, then the length of the conductor times the magnitude of the magnetic field, and then the angle between the conductor vector and the magnetic field vector. So this is the angle phi here. So these two operations will give you both the direction and the magnitude of the force acting on a conductor that has been placed into a magnetic field. In this situation, our L is directed like this. It's always in the direction of the conventional current, and the magnetic field vector B would be here. And now we want to evaluate the direction of F. So we have to cross L and B. To do that, we point our right hand fingers towards L, curl them towards B, and in this case our thumb ends up pointing into the screen. And that is the symbol for that. So that's the direction of our force in this case. The magnitude would be I times L times B, and then the sign of the angle between these two vectors, which in this case is theta. Now a couple of more exercises. In the first one, we have a wire carrying current I, and it is perpendicular to the magnetic field of strength B. So, for example, I goes like this, and the magnetic field is like this. Assuming fixed length of wire, which of the following changes will result in decreasing the force of the wire by a factor of 2? So we want to see what happens to the F, which is the magnitude of the force, if we change some parameters. First, decrease the angle from 90 to 45, so that would affect this term. If sine 90 becomes sine 45, that doesn't decrease by a factor of 2, it will decrease it by a factor square root of 2. Okay, what about B? Decrease the angle from 90 to 60, so yeah, 90 to 30. So sine of 30 is half, so yes, that is true. What if we decrease the current in the wire from to I per 2, so we halve the current, so yes, that will halve the force as well. And what about decreasing the magnetic field strength to B over 2? Well, yeah, that does the same thing. So B, C, and D. In exercise D, we have pretty much the same case as here. We have a straight power line carries current 30 amps, and it's perpendicular to the Earth's magnetic field. So the magnetic field is perpendicular to the power line. What magnitude force is exerted on 100 meters of this power line? So we use this same expression, so I times L times B times sine theta, and I is 30 amps, length is 100 meters, magnetic field strength is that of the typical value of Earth, 0.5 times 10 to the minus 4 Tesla, and sine of the angle between the two, which is 90, so that's sine 90, which is same as 1. So this turns out to be 0.50 newtons, which is not a whole lot on 100 meters of cable or conductor. So it's not going to cause any structural trouble.